start it up again. All right, I want to talk about another application area where optimization plays an important role, and this is a statistical thing. So I think this one is this topic is probably especially close to the kinds of things people in machine learning are interested in. So there's many things one could talk about, but I just want to talk about something simple: regression. And I want to compare least squares regression to least absolute deviation regression, and show you how least absolute deviation regression can be solved by linear programming. And in the end, this might actually get deferred until Monday. I want to do a regression analysis of the parametric self-dual simplex method, the number of iterations as a function of problem size for the algorithm I just showed you. To motivate all this stuff, and I hope it's not too elementary, but I thought I would give a little introduction into means and medians and how they're related to regression in general. So I wrote my book 17 years ago, and so I took some data that I was able to find on the Internal Revenue Service's website in the United States of adjusted gross incomes on individual tax returns. So this was several million data points. I forget exactly how big M was, but it was a bunch of data points, and for each individual, it was gave their adjusted gross income. That's the income minus various deductions that you're allowed. So there's just 5 people. The actual data that I got from them is summarized here. In fact, this is the data I got from them. I didn't get all several million returns. I just got this little table. And in this table, it tells you how many, this is the number of returns, and this is the adjusted gross income. So the total adjusted gross income is this, and this is in thousands of dollars, is it? Yes, in thousands of dollars. So let's see, that's 5,000, 5 million, 5 billion, $4 trillion divided by 118 million returns would give you the average income in the United States. But the table that I found interesting was that they broke it down into categories and told us how many people in these different, how many returns in these different categories, and the total in each of those returns, in each of those categories. And so you can use this to find out what the median income is, and I think I have it on the next slide. But the median, of course, is the middle person, and it's a little bit, so you just start counting these up here. There's 900,000 here. Well, we want to get to 118 million, so we want to get halfway. So this is about a million. That's about 15 and a half. That's 15, 28, 30, 41, 53. So somewhere around here is the halfway point on our way to 118 million. So the average adjusted gross income 17 years ago, I think, was somewhere between $20,000 and $25,000. So here's the actual number. Well, so I don't know. I can't deduce from that table the exact median, but it's somewhere in that middle range. In that middle one. I mean, not in that middle one, but in this 20 to 25,000 range. And so I just took the middle of this. And got 22,500 as the median, as my estimate of the median. Whereas the mean, if I add up all the numbers, that was that 4 trillion, and divide by the total number of returns, that was 118 million here. That's $35,473, and that's a dramatically larger number than this one. And that's because there were no negative numbers, but there were some really big positive numbers. And so this is a highly skewed distribution, which is why I picked it, to illustrate that means are sensitive to asymmetric distributions, outliers, if you like, although those very rich people might not be exactly outliers. The data is not wrong, it's just disturbing. Anyway, so how is this related to linear programming and all that? To compute the mean, well, you can define it as the solution to an optimization problem. We minimize over all x the sum of the squared deviations from the data points, bi. Why does this give us the mean that you are familiar with? Well, let's just check it with calculus. We write down the function f, the sum of the squared deviations. We take its derivative, which is quite simple. We set the derivative equal to 0, and the value of x that achieves that zeroness will be the mean, x bar. So we get a formula for x bar, put x bar here, set this equal to 0, solve that equation for x bar, and you get x bar is 1 over m, the sum of the b's. And of course, it's a minimum, not a maximum, because this is convex, or if you like to say it differently, as you go to plus or minus infinity in x, this goes to plus infinity, so this is definitely a minimum. Okay, freshman calculus, just solve the problem with calculus. All right, what about medians? Medians are actually the minimum of the sum of the absolute deviations. Okay, we can still do calculus. It's a little bit tedious because you don't like differentiating absolute value function. But we can do it. So here we write down the function f, we take the derivative. The derivative of the absolute value function is quite simple. It's either 1 or minus 1. And okay, yeah, there's a place at 0 there where the derivative doesn't exist technically. But basically it's 1 or minus 1, depending on whether you're bigger than bi or whether you're less than bi. And I don't know how standard it is, but the signum function some people use to represent the function that's 1 when its argument is positive, and minus 1 when the argument is negative, the sign of the thing. Or if you just want to write it out in words, it's the number of bi's that are smaller than x minus the number of bi's that are larger than x. And we would like to set this equal to 0. This will be equal to 0 when the number of bi's that are smaller than x is equal to the number of bi's that are larger than x. Or if you want, you can plot this function f prime, and it crosses 0 at some point. It crosses 0 at a data point, which is if m is odd, it jumps from minus 1 to plus 1 exactly at the median. So, okay. All right, let me go back. Okay. So, I want to do a regression model, which is a generalization of means and medians. And so here's the model I want to introduce. I want to study the parametric self-dual simplex method and how many iterations it takes as a function of, I don't know, let's say m plus n. So here's some real data. These are real problems that were collected by David Gay back in the mid-'80s and early '90s. These were considered difficult by the people who've made these problems. These are linear programming problems that were considered difficult. And they come from different places. So A.D. Little's Arthur D. Little, the finance company. Boeing is the aircraft company. Beacon FD is the Beacon Fire Department in Boston, I think. Beacon Hill Fire Department. I used to think this was band M. No, well, now I forget actually. Is this B and M or band M? I think it's B and M, and I don't know what it is. I used to think this was brandy, but actually it was brand Y. These SCSD are staircase structural design. So these are the kinds of problems that I was just showing you, actually. We are building a structure with beams and nodes. So we have a wide variety of different problems here. Interesting. Seems like some of them are missing. Anyway, maybe they're over here. Here we go. Yes, Israel was one from the Israeli Air Force. I forget, forestry planning problem, I think it was. I forget what the Shell Oil Company. All kinds of different problems. So we want to make a regression model. And so the data that I just showed you is a bunch of values of number of iterations, which I'll denote by t, number of constraints, which I'll denote by m, and number of variables that I'll denote by n. And those number of iterations were all computed using the parametric self-dual simplex method as programmed by me. And so we want to make a model. Here's the model. We want to say that the number of iterations is some constant, some positive constant, which I'll write as 2 to the alpha, times the sum m plus n to the power beta for some beta. And alpha and beta are my unknowns here. I want to find the best approximation. And what we do is we take the logarithm of both sides, and we say that the log of t is equal to alpha times the log of 2, that's from that one, plus beta times the log of m plus n, that's that one there, plus some epsilon. The epsilon's not a random error. The data is perfect. I implemented the algorithm, I counted the number of iterations. But we don't really know what the world of, I mean, in some sense it's random. Those problems were drawn from the world of real problems. And I don't know what the probability distribution on that world of problems is, and so I don't really know what the probability distribution is on this epsilon. But anyway, this is our regression model. And I have a bunch of data. And so we set this up like this. I got all my data here. I'm going to call that B. I've got my coefficients alpha and beta. I'm going to call that X, because that's the way I am, like linear programming. My variables have to be X. Statisticians do this all differently. I think the A matrix is called X. Very confusing to me. Anyway, the A matrix is the data, but as it appears in my model, it has log 2 for the first thing all the time, and so that's the same constant everywhere in this column, and then we have log of m1 plus m2, m1 plus n1, and m2 plus n2, and so on. So the second column varies from problem to problem, and then I've got these epsilons, which will be different. So this is my model. B equals ax plus epsilon. The problem is to find the x that minimizes the epsilon. In some sense, I put the minimize in quotes because there's a variety of ways of doing this. So, one way is to do standard least squares, every statistician's best friend. So we use least squares. That means we're taking a Euclidean distance, the sum of the squares, square rooted, if you like. So least squares is the square of that Euclidean distance. We want to find the x that minimizes the sum of the squares. We can solve this problem with calculus, just like we could with the mean. And it's kind of useful to go through this little calculation. So the function we want to differentiate is the sum of the squares, which I'm writing out in all of its gory detail here. And we want to differentiate this. This is multi-parameter, multi-dimensional, so I've got x1, x2, etc. Actually, in my real problem, I just have alpha and beta, so there's really only 2 variables in the problem I want to solve. But in general, I have lots of these variables, up to n of them. So I differentiate this with respect to each of the variables and set it equal to 0. And when I set it equal to 0, that's going to give me the thing that's the analog of the mean, so I put a bar over it. So when I've solved this equation, that'll give me the least square solution, which I'm denoting by x bar. And it's a vector, so x1 bar up to x whatever bar. Okay, so we rearrange this equations here. So I'm setting this equal to 0. The 2 I can divide both sides. That goes away. And so on I have a sum of bi times aik, and that has a minus sign, which just means I can put it on the other side of the equation if you like. And then the other part, I have a double sum, and I have a double minus, which makes it a plus, of aij, aik, xj bar. So a double sum, aik, aij, xj bar. And so, going back to matrix notation here, this sum here, because I've got aik, bi, I really want to have I'd be happier if this were aki, but it's not. It's actually aik. So I have to take this is actually the transpose of the A matrix times the B vector. So that's that. This double sum, if you think about it, again, I would like to have this be AKI, but it's AIK. If it were AKI, this would be KIIJ and J. So that would then be a matrix vector product kind of thing. So that's A transpose A times X bar. So you get this equation. And the matrix A transpose A should be invertible. That would be an assumption, I guess, to do this regression. And you can then solve for X bar as A transpose A inverse, A transpose B. That's probably a formula you've all seen before, I'm guessing, if you've taken a regression course, and I'm guessing most of you have. I presume that that's familiar. Let's talk about least absolute deviations. It's similar to the kind of parallels we had with means and medians. So now we have the sum of the absolute values instead of the sum of the squares. So that's the L1 norm, if you like. So we can write that way. And so I introduce the function f, which is the sum of the absolute deviations. I do exactly like before. I take the derivative. But now I'm taking the derivative of the absolute value function. And I've chosen to write that in this way. The derivative of the absolute value of x, the derivative of the absolute value of x can be written as x divided by the absolute value of x, because when x is positive, that's 1. When x is negative, that's minus 1. And we're not going to worry about little places where the derivative doesn't exist. So this is the derivative. The sum of the derivative of that, which is this expression here, and then by the chain rule, we have to take the derivative inside. We're taking the derivative with respect to xk. This is a constant. It doesn't have, it gives us nothing. Then we get the minus sign, and as I take this sum on j, all of these are 0 because they're xj's, except for the when j is equal to k, and then I get aik. So that's right there is the derivative inside the sum with respect to xk. So we want this derivative to be equal to 0 at the value of x that achieves that. Well, I'll call it x hat to distinguish it from x bar. So that will be the analog of a median. It'll be the least absolute deviation regression coefficients. So that's what I get with x hat. And again, we break this up into two pieces, just like I did before. The b stuff on one side and the xj stuff on the other side, and I get an equation that looks like this. And it's kind of good and bad. It's good in that it almost looks like the equation we had before. And in fact, if we're careful, I should say, these epsilons I've written in the denominator are just these absolute value expressions here. So I've just summarized that as epsilon. I guess I forgot to mention that on the slide here. So, except for those epsilons, this is exactly the same thing we had before. And if I write this in matrix notation, this is how this appears. The epsilon I, because it depends on I, goes between the A and the B, because that's A transpose Ki, then it's this, then it's Bi. And similarly, I forgot the I there. Two typos. Yikes. This is supposed to be epsilon sub I also, and it goes between the A, Ki transpose Aij. It goes in there. And so if we write this in matrix notation, it's A transpose E of x hat times B, where E of x hat is a diagonal matrix with these epsilons along the diagonal. It's the inverse of that diagonal matrix. So it's the diagonal matrix is 1 over the epsilons on the diagonal. That's exactly accounting for this factor here. And the same thing appears on the right-hand side. It appears between A transpose and A. So again, assuming that the matrix multiplying the x is invertible, in this case it's this thing, we can solve for x hat. X hat should be equal to the inverse of that matrix times A transpose E, of x hat. Now that's a problem, isn't it? X hat appears on the right and on the left. And I suppose this is part of the reason why statisticians like least squares better than least absolute deviations. We don't get a simple formula here. We don't get an equation. We get a formula. This formula must be satisfied. But unfortunately, it's not an equation. It doesn't say x hat equals something that doesn't involve x hat. Rather, it's just some something that's true, an equation that's true, and we've got to find the x hat that satisfies this. There's two ways to find it. I'll give you a simple algorithmic way, and I'll also tell you how to find it by linear programming. And we can debate which way is better. So here's the simple method that avoids directly using linear programming. It's called the method of successive approximations. Comes up many, many, many places. Whenever you have something like x equals some function of x, some implicit function like this, you can always consider solving this equation by saying, okay, I'm going to start with x being equal to some guess. What's the simplest guess? Anything you like? I'll just say 0. This will be my first guess. And then I can update this guess. I can say, well, look, maybe that's a better guess. x1, let the x1 be f of x0. You have to prove it that it's better. It might not be, but it's certainly a reasonable thing to do, to suggest. And then maybe, if you keep doing this, maybe it gets better and better. And keep doing this forever, and take the limit. And if f is continuous, and if the limit of the x's exists, then you would have this equation, which would say that x infinity is the thing that you want. So it requires us to assume that f is a continuous function. It requires us to assume that we can prove that the sequence of x's has a limit. And if you can prove those two statements, then this process gives you an answer. It gives you an answer in the limit, though. So the complexity here is, well, technically speaking, you have to run this algorithm forever. But, you know, in practice, we do everything in finite precision arithmetic anyway. So even all those beautiful algorithms that converge in a finite number of iterations are subject to small errors themselves. And so to be honest, when you get within some small epsilon of the right answer, you should be allowed to shut this down and say, I'm now there, and that would be just as good. But it's hard to know how many iterations of this you need to do to guarantee that you're within some given a priori estimate epsilon. So that's the upside and the downside. It's easy. Each step is a regression problem. You're just this is called iteratively reweighted least squares, because each of these calculations is solving a weighted least squares problem where the weights depend on your current estimate. And then you just keep reweighting it as you go. And you can prove that this is convergent fairly generally. But it's not linear programming, and so I won't dwell on this algorithm. I'd rather go to the linear programming algorithm. All right. How do we model this as a linear programming problem? Well, just like the one before with our structure and the hanging weights, we have absolute values here. And I'm going to do a slightly different trick, but the takeaway message is whenever you have absolute values, you should say to yourself, I can probably make this a linear programming problem. So here's the trick here. It's similar but different in the details. So you look at this thing, and I used to teach calculus, and I would teach methods of integration. And in methods of integration, I would tell my students to use the greedy substitution, by which I meant take the ugliest thing you can find in the problem and give it a new variable name and substitute it out. And that's exactly what we want to do here. The ugliest thing for us is the absolute values of this thing. So give it a new name. We got a bunch of these absolute values. They're indexed by I, and so a new variable ti for every one of these absolute values. Now I would like to say that ti is equal to the absolute value of this difference. That's the truth. Ti should be equal to that. But now I'm going to be a little bit clever, like we were a little bit clever before with the absolute values, and say, okay, that wouldn't be good to write equals absolute value because I haven't made things better. But how about if I say, look, if ti is bigger than the absolute value, if ti is bigger than or equal to the absolute value, then ti would be bigger than this expression, And negative ti would be less than this expression, because we want to squeeze it on both sides. And that would be true if ti is bigger than the absolute value. And that relaxation is okay because I'm trying to minimize the sum of the ti's. And so I'll never leave slack, again, that's the same kind of idea. I never leave slack in both of these inequalities. If I did have slack in both of those inequalities, then ti wouldn't be the absolute value. It would be bigger than the absolute value. I want to pull it in tight in every case. In the cases where this is positive, I want to pull it in tight on the right. In cases where this is negative, I want to pull it in tight on the left and leave no slack on one of the two sides. And because I'm minimizing, I will never leave slack on both sides. And therefore, at optimality, the ti's will be the absolute values. So it's essentially the same trick I showed you before. And that's a linear programming problem. We can solve it with the simplex method, if you will. So, here's another ample model. Why not? Just spend a few minutes on it. This is the ample model for linear least absolute deviations regression. So we've got two parameters, m and n. Those give us the size of the A matrix. So I've got a set I of indices, of I indices. I didn't have to write it this way. But anyway, I goes from 1 to m, j goes from 1 to n. Then the A matrix is a matrix, so it's two-dimensional, so it's indexed by i's and j's, I comma j. The data b is just indexed over the i's. I have the original x variables. They're still in here. I didn't get rid of them like I got rid of them in the other model. I still have the original x variables, and they're indexed by the set j from 1 to n. The new variables, the ti's, they're indexed by the I variables in the set I. And then I want to minimize the sum of the deviations, which is the sum over all indices I, t of I. And I had two kinds of constraints, the lower bound constraints and the upper bound constraints. I wrote them all in one line before, but in ample, actually, we have to split this out separately. So I have the constraint, subject to. You have to give names to your constraints in this ample modeling language. And you can, of course, index your constraints. So this is m constraints written on two lines. And so the constraint was that minus t sub I is less than or equal to bi minus the sum on j of aij times xj. It's exactly the same as it was here. Except for here I have actual subscripts and so on. Here I have to use a little bit of brackets and braces, and you have to learn the syntax a little bit, but it's very easy. And I have to write the upper bounds separately. That's one of the things that ample requires. Ample also requires you to name all of your constraints. And you know why you have to name them? Because it requires you to. But the reason they require you to is because after you've solved the problem, you might want to know the dual variables. The dual variables are associated with the constraints. If I say print lower bound of 3, I will get the dual variable associated with that constraint. So that's the nice reason why ample requires you to name all your constraints, because that's how you get out the dual variables when you're done, if you want them. Okay, so we have a few minutes left. I want to apply that ample model to the data that I showed you before. And before I apply it, I want to take you through a little bit of a thought experiment, which is, I don't know, intriguing to me. Here's the thought experiment. This is about the parametric self-dual simplex method. Let me summarize how that method works again. We want to get to 0 on the mu line. And we initialize things in such a way that for mu larger than some threshold, we're optimal. And then we iterate. And after a while, we have an interval of mu's that is optimal. And we look at this lower bound, and then we do a pivot based on what caused that lower bound. And that makes it so that at the next iteration, we have a new lower bound. A new lower bound, and that upper bound, this position, which was the lower bound, becomes the upper bound of our new interval. So as we're walking our way towards 0, it looks like this. We have n plus m inequalities. And because we do the simplex method correctly, all of the inequalities that are to the left of this lower bound are pointing to the right. And some of them are way over here, some of them are negative, way out here somewhere. But all of them are pointing to the right if we're below this place. And all the ones above this place are pointing to the left. And we got a whole bunch of them. When we do a pivot, the element that we pivoted on, that inequality only flips to being from a lower bound to an upper bound. All the other inequalities change in ways that are very hard to predict, because it's all about the algebra that you did and all the linear combinations of all those rows to do the Gaussian elimination kind of thing, to do a pivot. All these inequalities come out looking quite a bit different after you do one pivot. And it's hard to predict, but there's still n plus m of them, and they just move around. Who knows how they move? This one might have landed way over there, and this one might have landed way over here, and this one here. The only thing we know is because we did a legitimate pivot, all of the ones that are to the left of this place point to the right, and all of the ones that are to the right of this place point to the left. And this particular place points to the left. And, okay, so here's the thought experiment. How many iterations should this algorithm take? If those barriers didn't move and just stayed put, well, then I would say, look, I'm putting n plus m numbers on this line at random. Probably half of them are positive and half of them are negative. I don't know what the data of the problem looks like. Why should I think anything else? And if half of them are positive, each time I do a pivot, I go open one of the doors and go past it. It would take n plus m over 2 pivots. But of course, those thresholds do move every time I do a pivot. They change in highly unpredictable ways. But why should I ever think that there's somebody conspiring against me to keep getting in the between? When they fall between 0 and wherever I am, that's bad. Lots of them are falling between me and 0. That means I have to do lots of iterations. If they all fall either to the left of to the negative half line or above where I am, then I'm done. But why should they know where I am and how far I have to go? There's no conspiracy. It's just a random problem. And so even though they're jumping around, it seems to me that on the average, they haven't really gotten in my way or out of my way, and I probably still have to take n plus m over 2 iterations. So this is my conjecture. I don't know if it's true in any rigorous mathematical sense, because I don't know what probability distribution to put on the space of problems to even attempt to do this calculation. If somebody, one of you, were to come up with any reasonable probability distribution on the space of A, B, and C, the data of the linear programming problem, and with that probability distribution prove my statement is correct, I would be very happy. Even more than that, I think you'd actually be rather famous, because it's, I think, a good problem, and it might be true, and I don't know. So, rather than spending my whole life trying to prove it, I went to empirical studies. So I took those problems that I showed you and that data that I showed you, and I ran this regression model. Actually, I did it both ways. I did least squares and least absolute deviations. And I got, since there really weren't any dramatic outliers, I got very similar answers in the two cases. When I did least squares, I got that the number of iterations was 0.488 times m plus n to the 1.052. That looks surprisingly close to 1/2 m plus n. And when I did least absolute deviations, I got a similar answer, surprisingly close to So 1/2 m plus n. Very surprisingly close. And I don't know, actually, if that's just luck, a coincidence, or if there's something fundamental. The problems that were collected for that collection that David Gay made, the NetLib suite, the problems that were collected for that were thought to be hard problems at the time. So I don't know. I showed you this morning some other randomly generated problems and how well just the primal simplex method did, and the power was not to the power 1, it was to the power 4/3 approximately, or something along those lines. And so I don't know, maybe that was better, or don't know. Interesting research question in my opinion. Okay, so here's a plot of the answer. Those are those NetLib problems. This is the size, m plus n, going from less than 100 to, like around 50-ish up to about 10,000. So there's a pretty wide range of problem sizes. They were all considered to be hard. And here's the number of pivots it took on a logarithmic, on a log-log plot. And it does look like a straight line going through there. Seems like a reasonable thing to do. I mean, there's some deviations. If this had been over here, that might have been an outlier that would have made the least absolute deviations regression look different from the least squares regression. But because it's somewhat near the center here, it didn't really have a significant impact. And so the two lines, the red one is least absolute deviations, and the blue one's least squares. They're about the same in this particular example. So I don't know. That's that. So I also more recently generated my own random problems rather than relying on this NetLib suite, and ran them, and I got a plot that looks a bit different. And I don't know how to reconcile this plot with the previous one. I generated these randomly, and I'm not showing the code here, so we don't see exactly what I did. But it's similar to what I had before with generating with Gaussian, independent Gaussian coefficients in the A matrix, and something similar to that for B and C. And anyway, you can see that, again, some problems are actually easy. As I explained this morning, that's kind of understandable when M and N are very different from each other. And in the problems from the NetLib suite, that's never the case. These problems all had N and M of the same order of magnitude. There were no problems with, N equals 500 and M equals 3. It just didn't happen because those problems aren't hard. So this lower part gets whittled out of that NetLib suite from the condition that they wouldn't have been sent to David Gay if they weren't hard. But nonetheless, I do get a regression line here that looks kind of similar. It looks about like 1/2 m plus n, not as close as before, but also this regression line looks like it's being biased by these low numbers. It looks like it should be up here more, and it also looks like it should be steeper. So the power does look like it should be a little bit bigger than 1, but the coefficient here does look like it should be approximately 1/2. So anyway, I wanted to show you all these things to give you some idea of the average complexity of the simplex method. The takeaway message is, the easy message to remember is that, roughly speaking, it's probably about 1/2 m plus n pivots to solve a problem of size m and n. Okay, and I also made the plot with the m min n to sort of account, as I discussed this morning, that is maybe a better measure where we generate some of these artificially easy problems. And actually this does look quite beautiful, and the line goes through it beautifully. And now it looks like 1.5 times the minimum of m and n to the 4/3. So that's looking similar to what we saw before. Anyway, that is such a good regression line that I really think there's some fundamental theorem that one can prove, but nobody's proved it yet. So, okay, I think that's a good place to stop. And on Monday, we'll talk about interior point methods for linear programming and then for nonlinear programming. Thanks.